I just love isometric games. Maybe it's just nostalgia, but there's just something about the hand-drawn art style with the illusion of dynamic 3D that I just find really appealing. So in this video, I'm going to show you how isometric coordinates work, and I'll take you through the math to project an isometric grid into screen coordinates and back again. So let's start with a simple case. In a top-down 2D game, we might have a sprite asset that looks like this. It's easy enough to tile this asset across the screen. Just use multiples of the tile size and everything looks fine. But it's when we try to add some perspective for the 3D effect that things get a little weird. If we draw a 3D box on a grid like this, it looks fine. But if we now move that same asset around on the grid, it doesn't look quite right. This is because of perspective. Things closer to the point of view look bigger than things further away. This is a problem for hand-drawn art because we would need to draw infinite assets for infinite positions to move them dynamically. But if we just move the camera back really far away and zoom in at the same time, the perspective becomes virtually unnoticeable. In fact, if we move the camera back infinitely far away, there's zero perspective distortion. We call this an orthographic projection. The key here is that all the lines are parallel. Let's take a look at a hand-drawn isometric cube sprite. Taking a closer look, you can see where the grid would line up against this cube. For every 2 pixels on the horizontal axis, we move vertically by 1 pixel. Now this cube looks fine, so what if we try and tile it like we did before? This would make a nice bathroom wall, but it's not quite what we're looking for. The problem is that we need to transform the coordinates of each sprite to align it with the isometric grid. We'll start with our isometric grid and draw 2 lines. One to represent the length of a single grid tile in the x-axis, I hat, and one for a single grid tile in the y-axis, j hat. What we need to do is visually distort this grid. First we'll rotate it by 45 degrees and then squash it in half. The original grid is shown underneath because we'll need that next. To represent this distortion numerically, we now need to measure I against the original grid. I moves along the x-axis by a single tile just as before, but it now also moves down the y-axis by half a tile. So we can write that out as a 2D vector, or 2 numbers. Following the same process for j, we see that it moves in the negative x direction by 1 tile, and down by half. Now these 4 numbers are everything we need to describe this transformation of our grid. We can now multiply any x coordinate on the isometric grid by I hat and the y coordinate by j hat and add them together to get the screen coordinate. For example, say we wanted to find where grid coordinate x3, y1 would appear on screen. We multiply 3 by I hat and 1 by j hat. This gives us a new 2D vector representing the screen coordinate. And much better. But we're not quite done. You'll notice at the top left, the origin of our isometric grid doesn't quite match the top left of the screen. This is because the origin of each tile actually appears in the center of the sprite, not on the top left. So we need to account for that by offsetting everything by half the width of a tile sprite. And finally, we can offset the origin of the grid to the center of the screen. Okay, so we've got our isometric grid, but how about interaction? If we wanted mouse interaction, we'll need to go the other direction, to take the screen coordinate of the mouse and calculate which tile is being selected. Fortunately, maths can help us again. To add some depth, we can offset the screen y coordinate by some amount as a sort of third dimension. So I hope you found this useful. If you want to go into the math in a bit more detail, check out 3 Blue 1 Brown's excellent video on linear transformations and matrices. That whole series has a lot of great content.